Okay, so in this video we will be talking about possible solutions to actually solve the offline RL problem. There's actually two different kinds of ways how we can actually approach the problem. The first one is policy constraint methods, and the second kind is conservative methods. How do they actually differ, both of them? So in policy constraint methods, we actually tackle the problem that we have seen in the previous video within the policy improvement step. So we want to actually, or in other words, we want to actually keep our policy pi close to our policy pi beta. So the behavior policy that is actually used to collect all the data. And for that, we use a distance function pi, or a distance function over pi and pi beta. And the main problem is, how can we actually, or what can we actually use as a distance function for those two policies? And there's actually two things we will be looking at. And the first one is we want to match the distributions that our policy is actually inducing. This is then the algorithm called batch constrained Q-learning. So we want to constrain our policy to the data that the policy has generated in our batch. And we will then see is that there is also a limitation with BCQ, and then talk a little bit about bootstrapping error accumulation reduction, BEAR, which is not really matching the distribution, but is more resorting to kind of support measure to actually restrict the new policy with respect to the data from the policies that generated the data in our data set. On the other side, there is the conservative methods. Conservative methods, like conservative estimation methods, they tackle the problem in the policy evaluation step. So in the policy evaluation step is basically, they are addressing, so they want to actually estimate a Q function that is conservative with respect to the Q values. So if we are uncertain about the Q values, so this is the main motivation behind, in areas of the Q function where we have a high uncertainty, we want to really try to only get a decent lower bound of the Q function, and like we want to actually reduce the overestimations in our Q value. So we want to really get a lower bound of our Q function, and if we have a lower bound of our Q function, we really can apply the greedy policy improvement, because our Q values are always lower bounded. So this is the other thing. So in this sense, we see one algorithm called conservative Q learning, which actually learns this lower bound for the true Q function. Then we talk a little bit about MOPO, so model-based offline policy optimization, which learns something like a pessimistic reward function from which we can then estimate the Q function. And we, or actually that uses then also pure active RL strategies to learn from this pessimistic reward function. And then a more recent algorithm called Combo that learns a lower bound for the true Q function and uses also additional data from a model that is being learned from the data to actually augment the training process. Okay, so let's start with policy constraint methods. And maybe before we start in how BCQ is actually working, let's maybe formalize a little bit what or how we can actually tackle this problem. So the problem in, that policy constraint methods are really addressing is the problem that arises during the thing that we are bootstrapping the maximizing action, so that we take a not bootstrapping, so that our policy is actually sample the action that we sample from our policy is actually the argmax of the Q function. And this might be, we might do this without like considering any uncertainty we have in our Q function. So we actually bootstrapping an action, or we actually selecting an action where our model has a positively large extrapolation error. That this is actually wrong, because we don't really know much about this action. And the idea is basically to find an admissible set of policies, pi epsilon. And this basically means that there is certain policies that lie within an epsilon distance from the policies we have in our data set. So D is the distance measure, and we want the distance for all the policies that we define to be part of our admissible set to lie within this distance epsilon around the policy around the knowledge of policies that we have in our data set. And if we define it like this, we just consider a constrained policy improvement step that looks a little bit like this. So the new policy is actually not the argmax over our over what our theta thinks, but the argmax of all the policies that lie within our admissible set of policies that are actually maximizing the Q value that we can expect. And so that's the basic idea of also that is actually BCQ and that is used by Bayer. And in order to explain how this works in practice, we will actually introduce BCQ along 3 steps. But before I do that, so BCQ is actually was introduced 2019, and the idea is actually to restrict the action space in order to force the agents towards being close to the close to the data that we have in our data set. And if the bootstrapped actions are close, then the extrapolation error will also be low. So we might extrapolate towards actions that are not part of our data set, but if they are sufficiently close, we have a low extrapolation error. So that's basically the idea. And we will actually explain it using 3 steps. So we came up with a tabular case setting, like doing something like theoretical BCQ. So this was not part of the paper, but I guess it's really nice to understand how it works. Then we will talk about BCQ with function approximation in the discrete case, and BCQ with function approximation in the continuous case. Okay, so let's start with the theoretical BCQ in the tabular case. So just imagine that we have an MDP and this is the state space, so we have different states we can encounter through interacting with the environment, and we have trajectory rollouts all starting from S0. There's 2 actions actually up and down, encoded with the 2 colors in here. We have a tabular Q function, so we can like really enumerate everything, and there is no reward so far. So we only want to consider visitation sequences in this setting. Okay, so and now consider our data set. Our data set could look like this. So we have transitions in our data set, and what we see here are the transition counts we have in our data set. So we have a behavior policy, and it might not select the down actions in these 2 states or in this state or the up action in this state. So the orange numbers in here are somehow the counts of the transitions that we have in our data set. And what we now want to do is actually, so it's finite and it's also deterministic MDP, making things a little bit easier. And what we can actually do to solve the problem is actually to say, okay, using this data set, we estimate the restricted MDP. And so we throw actually everything away that has not been selected. And this would be the resulting MDP. Nothing else can be selected, so nothing else is part of the data set. So we really don't get to that point. And we get the restricted MDP, so everything, we have knowledge about everything that happens in this part of the MDP. And then actually we could solve the restricted MDP. So we can use the data that we have and we can solve the restricted MDP, and we are sure that for every action, for every state we are encountering in Q-learning, and for every action that we have, if we just resort to what's happening here, we know that we do not bootstrap any out of distribution action. So all the policies that stay in the restricted MDP can be accurately assessed because everything is deterministic. So this could actually, so if you just count what data you have and you throw everything away, so this is the set of admissible policies. So all the admissible policies lie within that restricted MDP, and everything else is not part of your state and action set. And if you like solve the MDP on this restricted state and action set, you can just apply Q-learning and solve this. However, things get a little bit more complicated if we talk about stochastic MDPs. So everything was deterministic in the first case, so we knew that if we selected the down actions, we really get down, okay? and if we select the up action, there's no probability that if we select up, we go down. However, in practice, we have seen that during many reasons, it might also be different. So this is the same setting that we had in the previous example. However, we now have a stochastic MDP. So there is a certain probability in here that, so these probabilities are of course not known to the agent, but there is a certain probability that you select the down action, and with 75% you really go down, and with 25% you go up instead. So these probabilities are all equal for all the states. And if you now capture data, like if you do the counting again, so the orange numbers in here are the transitions count that you observed. So in this setting, you selected 5 times going up and 6 times going down. However, in 6 cases, you actually end up in here. In 5 cases, you end up in here. Because there is a certain probability where you really end up in a different state. And this is really problematic. Consider, for instance, this transition of this state. So you have an action that goes down in here, but due to the stochasticity in the environment, you really end up in this node. However, and if you select the up actions by chance, you actually every time visit this state, but you never really visited this state. And if you now use the data that you have in your transitions and you estimate the restricted MDP, and you solve the estimated MDP using Q-learning in here, the resulting agent, so it really depends. So it really depends on the number of data and your diversity in your data. But depending on the quality of the estimation of your MDP, it might happen that if you deploy this agent might actually be swept into the unknown. So there is a chance that you optimize in this setting in here, and you can select the down action in here, which in this restricted MDP always leads you to this state, but in reality might be getting you this state in here. And this is really problematic, or in this sense, there might be a probability where you think that you're coming up in here, but you don't have the down action. So this might also be problematic in practice. So if you have a stochastic MDP and you do the restricted MDP estimation and you solve it using something like Q-learning, if you deploy it, you will see a distribution shift. Basically, that's what's happening because you have a wrong estimation, and the agent would actually swept into the unknown, and you will see a situation that you will not have encountered during training. Okay, so what's basically the idea, or what can we actually do out of it, or do with the knowledge that we currently have? So in Q-learning, so this is actually the Q-learning loss optimization. So in Q-learning, we want to actually minimize this mean squared Bellman error in here. So we want to minimize the reward plus the maximum Q value we can expect with actions in the next state. And now let us define, and this is actually the problematic point in here. So let us maybe at this point define a restricted action set that we might bootstrap our action to. And the restricted action set is actually called ABCQ, A epsilon to the power of BCQ in here. And we define it like this. Part of this action set is any action from our real action set that is actually satisfying this equation. So we actually want the probability of this action being selected with respect to the maximizing action to be larger than a certain small error in here. So we want actually to be our action set. So we want to have actions that are not represented much with respect to other actions. We don't want to have them as part of our action set. So this is actually what's the meaning of this of this term. And epsilon is something between 0 and 1, so it couldn't be larger than 1 because actually some action is maximized, and it's really a normalized value between 0 and 1. And both of them are the estimates of the behavior policy from the data that we have. And we can then define a constraint target, and the constraint target is actually not the alpha prime being part of all the states, but only about along the restricted action set of our states. And we only consider the actions where we have high enough probabilities of being selected with respect to the maximal probability of the actions from the action set. If we take an epsilon of 1, we only will select the action that maximizes the action set in here, so that's maximal. This would actually be a behavior equivalent to being a behavior cloning. So we really want to imitate what the behavior of the policy that generated the data is, if it's from one policy, and if epsilon is 0, we would have any action to be admissible, which then reduces to the standard Q-learning setup, because actually then both action sets became equal. Okay, so we actually introduce this constrained action set in here, and then the learned policy is just pi s being the argmax over the restricted action set. So this is actually where we constrain the policy in the policy improvement step. However, problematic in practice is, so this would be the motivation. So this is like, in theory, the thing how BCQ works. And however, the problem is in the continuous case, so this works for the discrete case, you can just enumerate everything and you can just calculate everything, but you know that, and you can actually also recap that, you can actually come up and do that with a grid world example. You can really enumerate all the state transitions, you can estimate these values, and then you can run BCQ on that and really see how this works. You can also come up with this AND environment where you actually have all that things in, and you can apply BCQ. However, it is not so easy if you do that in the continuous case, because computing this restriction in the continuous case is not that straightforward, because you actually have an infinitely a large amount of states in here, and this actually is problematic if you want to really estimate this ratio value in practice, because it's actually intractable to do that. And in order to do that, BCQ actually addresses this using 3 components. And the first component is actually a conditional variational autoencoder. So a variational autoencoder is a special variant of an autoencoder that lets you sample from a latent space using a prior, lets you sample a variable, a value using a probability variable, and then you can actually sample from a latent distribution, so you can actually sample actions. So this is the conditional variation autoencoder. We will see it in a minute why it is conditional and how is it actually conditioned. Then it additionally uses a perturbation models that improves actually sampled actions. So we sample an action, and we want to actually improve that action in a local neighborhood. So we want to maximize the action, but we want to only do that in a local neighborhood where we are sure that there's low extrapolation error. And we apply soft-clipped WQ learning to fight the overestimation in continuous action spaces. But maybe let's look a little bit at all these 3 components in here. So this is the first component. It's the CVAE. And the goal of the CVA is actually to sample from a behavioral policy. So the idea is that we have the data set, and we train on this data set a conditional variation autoencoder, and the idea is that the conditional variation autoencoder exactly gives us pi beta of the action. So it exactly gives us this value. Because this value is actually something, or this value here, these values, both of them, they are actually intractable to be computed in a high-dimensional state space. And what we could count in the discrete space, we cannot really count it in the continuous space. And this is what we actually want to counteract with the CVAE. So the CVAE is actually giving us something like a density, or like an idea of how likely the behavioral policy actually chooses samples and action given a certain state. So pi beta of S is unknown and difficult to sample from, and they use a conditional variation autoencoder. So how is it trained? So we have state action pairs as part of our data, and we train an encoder. So you maybe know how a VAE looks like. So deep learning was somehow the prerequisite of this class. So you have incoming data and outgoing data, and you want to push them through a bottleneck. This is the standard autoencoder. And in the VAE, you actually want to have the bottleneck to be represented as standard Gaussian normal distributions from which you then can sample from. So you want to actually represent your input data using a multinomial Gaussian distribution in the bottleneck. And if you have a multinomial Gaussian distribution, you will sample from that distribution and you get an output from the data. This is the current VAE. The conditional VAE looks a little bit different because it actually conditions on certain variables. So the input in the encoder is similar to a VAE. So we have the state and actions as an input. So this is part of the transitions we have in the data set. And we get some random variables in here from which we want to sample finally. And we actually, during training, we sample from those from the latent space, condition on a certain state, and we want to estimate the action that we want to take in that state. And this is actually, again, the ground truth from the data set, and this is the ground truth from the data set, and we actually want to ensure that the data lies within a standard normal distribution of several Gaussians in here. And if we do that, we can actually condition the variation autoencoder on a certain state and just sample an action from that distribution. So this allows us to really approximate pi beta given S for all of the actions that we might take. Exactly. So this is the conditional variation autoencoder. It just somehow lets us approximate this value to in order to calculate the restriction within the epsilon bound. A second one is actually we get the density, or we actually get, if we sample from our conditional from our CVAE, we obtain sampled actions. So we sample a lot of times from our CVAE, and we can actually estimate the probability of those actions. So in a state S prime, we have obtained sampled actions A prime from our behavior policy that somehow matches the distribution of our data set. And the problem is now, if we want to find really a good action, so if we really want to estimate how, if we want we actually want the maximum. So we actually want the action that maximizes this function. However, we need to sample a lot in order to get a decent estimate of the probability distribution of the Q function in S prime. And the idea is here to use a perturbation model to improve the Q value in a local, so in actually to search around the local neighborhood to search a good action. And the basic idea is to have a perturbation model and apply DDPG. So we have seen DDPG in the policy gradient lecture. And what they actually are doing is they search in the local neighborhood the action that maximizes the Q function. So this is in order to actually in order to reduce the need to sample like infinitely many actions from S prime in order to get the maximum, the maximizing action. And the third component is soft-clipped double Q learning. So the problem is that we have this perturbed actions A prime resulting in some A star prime, some maximizing action. And the problem is we have seen that we could actually use double Q learning. We have seen that in the DQN lecture, we can actually use double Q learning to fight the overestimation bias. However, they have seen in this paper that at points, especially in the supervised setup, the two networks that we usually have become too similar. And if the networks become too similar, the idea of double Q learning in this sense doesn't really work then anymore. And the idea here, it's only a minor contribution, is just to use a convex combination between the minimum and the maximum Q function. And basically this lets us actually give us an idea to actually penalize regions of uncertainty in the network, because we actually have, this is somehow the idea of an ensemble. So in areas where you have high uncertainty, these values become large, and this actually gives us a way to penalize regions with the Q values are uncertain, and this can be used then to fight the overestimation error with in Q-learning when we approximate the Q function. Okay, so these are the three components. The CVAE, in my opinion, is the most important thing, and the DDPG then is actually being used to really search around the actions to reduce the need to sample so much actions from the state space in order to get the maximizing action. So this is the pseudocode of BCQ. So the input is the data batch, so it's our data buffer. We have horizon T's. This is we run in T iterations. We have target network update rates. We have a mini batch size, things that you know from supervised learning. And what we have actually, we have we have Q networks. We have a perturbation network, and we have the variational autoencoder. We initialize them with random parameters, and also the target networks are initialized with random parameters. So then if we start over in the iterations, we just begin with sampling a mini batch from the data set, just like we do it in supervised learning. And using that mini batch, we train our conditional variational autoencoder. So this is this is the formula you usually see, that the variational autoencoder basically minimizes the KL divergence between a standard normal distribution and the data distribution in the bottleneck, with a regularization on the reconstruction error of the action. So we have on the left side the action is an input, and on the right side the action is an output, and we want to have a reconstruction error be low, and in the middle we want to enforce that the data distribution in the middle becomes standard normal. So then we sample n actions from the CVAE, and we perturb those actions in the epsilon boundary, and using the DDPG algorithm. And this actually lets us define the target of our value function using soft double-clipped Q-learning in this sense. With that, we can actually train our Q value. So this is then just our mean square. This is just our loss function for the mean squared Bellman error, and we can actually train the perturbation model for the DDPG model, and then we can update our target networks for the Q networks, and then we can start over again. Keep on training the VAE, sample from the VAE, and train the perturbation model and the targets. Okay, so if we do that, and we run that on half cheetah, so that was the problem that we had in the motivation. What we're seeing here is like 4 different scenarios. So in this scenario, actually, there is a DDPG agent that is trained for 1 million time steps, and they store all the experienced transitions, and they use then these transitions to actually create a data set with these sets and actions, and basically so there's sufficient coverage in there. And what you actually see is that you are applying all these different methods that we have seen so far. They really do not perform very well in achieving a really good average return. However, if you apply BCQ, you can really see that with half cheetah you can really solve the problem with in contrast to the other ones. The same also holds for Hopper and Walker. So you see that using BCQ, you really see you can really extract a well-performing policy. So one more thing, so they trained the DDPG agent. However, they added a lot of noise to the actions that the DDPG agent is actually producing. And what you see here is the behavioral policy means that the behavioral policy performs well, but there is not like a really performant behavior because the noise is so large, and they had this a large noise in order to get a diverse data set. So in the data set, the behavioral policy is actually not performing overly great. However, you can use this data set to actually create a policy that is outperforming the behavioral policy in this sense. Okay, so this is the concurrent performance in this setting. What they did is they trained off policy a DDPG agent, also for 1 million time step, and they still have sufficient exploration, so they actually put on top noise, but not that much that they did in this case. Because of that, the behavior policy actually keeps improving, also to a point of around 10,000 in the end, or 8,000 in this case, of reward. And all the data that the behavioral policy is actually observing is put into the replay buffer, and the offline RL agents are only using the data from the replay buffer to actually train. So they are trained along with the DDPG agent. However, they are not allowed to interact with the environment. And you see that in this sense, using the data in the buffer, you can see that BCQ is actually already outperforming the behavioral policy DDPG in this sense. However, you see that in many examples, for instance, in Hopper, they are really close to each other. In Walker, they're outperforming again. This is the imitation performance. So you train a DDPG agent that acts as an expert, and you use this expert data to collect the data set. So in the other examples, they used the data for training the DDPG agent in order to build the data set. In this example, they trained an agent with 1 million time step, and then they deployed the best agent, and then they let it run. They used this the only expert data to actually run the agent, and you see that only using the expert data as a data set, you will actually come very close to the performance of the expert policy. One more thing, so there is this VAE, behavioral cloning, which is a variant of behavioral cloning, of course. And if you like, in this sense, you see that usually behavioral cloning performs worse than offline RL in here. However, if you train from a top performing optimal policy, also, of course, behavioral cloning performs very well. But you see that offline RL also performs very well, or equally well, to the behavioral cloning policy, and both of them are very close to the expert policy in any of those runs. But really nice thing is the imperfect demonstration performance. What they have in here is they use data sets with only imperfect demonstrations. So the agents are trained on 100K transitions, so 100,000 transitions collected by an expert policy. And there's two sources of noise in there. So the behavioral policy selects actions randomly with 30% of probability, and they have a high exploration noise for the DDPG agent. And what you see is that in this case also, so you have an expert policy, but the data is not having expert selections in there. So the policy is perfect, but it is not selecting perfect actions. So meaning that the data set doesn't contain, or there's a high probability that the dataset doesn't contain perfect action selections. And you see that even in these cases, BCQ really comes up to a decent policy where you actually have so in this case you do not reach like the 8,000 or the 10,000 in here, but you really see that based on this suboptimal imperfect demonstrations, you can really use offline RL to come up with a policy that's really close to optimal. Okay, so I would say we stop at this point and we make bootstrapping error accumulation reduction part of another video.